Hi, this is Dwayne and Ali doing our assignment again. This is the code, a short walkthrough. We have a file that we call generic Q. This handles all of our Q code. There's a header file for it. It's a simple power of 2 circular buffer type 1. So here's the initialization code. We have functions to ask if it's full. We can protect the queue with interrupts disabled and enabled. What else can we do? We can do get next is full, is empty, get the used space, get the free space, insert, delete, peek into, don't take out, various functions like that. The generic queue code is used for both our event queues and for the file where we read into a buffer and take data out of the buffer. Everything is done through queues. In the event code, we have a routine that we call event send, and it's really simple. We go through, we have a small array of events. We allocate them by marking the event as in use. We have to protect that because interrupts can do allocation. Then, depending upon what type of, which part of the assignment we're on, part 3 or part 4, in part 3 we have only a single queue, so we just put everything in the high priority queue. In the part 4, we make 2 different queues, a high priority queue and a low priority queue. And we decided to put the button in the low priority queue because it's a mechanical thing and it's going to bounce. When we go to take data out of the queue, we have a routine SD card test. So here is our assignment number 2 code. This is what you see from the menu. The first time we come in, we initialize it one time. This is so that we can run the same tests over and over again. And if we're doing assignment number 2, or part 2, we do the super loop for parts 3 and 4, since they all do the event code. The first thing that we do is we send initialization events to our little state machines. Then we call the routine to do the events over and over again. The event code is really quite simple. Where is it at here? Here's the event code. We can stop our events from running if we press a key. So here's our test to stop the event code. Then we call a function to get the next entry out of the queue. And if we have something in the queue, we call the event handler. If you're familiar with the statemachine.com website, this is kind of like his linear state machines, but it's not, but it's kind of like it. So we send an event and we send the cookie data, or kind of like a void pointer, to the event handler. As soon as we finish with the event, we then release it, which lets it be reallocated again. Here's an example of a machine. This is the button machine. We get an event, we get data. We have events that we handle. Every time a button changes, we cancel our timer that's running in the background, and we restart it with a 100 millisecond timeout. We chose 100 milliseconds because it's just a handy number. Eventually, the button will time out, and at that time, the debouncing is complete. This simulation button is something that Ali used earlier for testing. We then read the button, which is really the GPIO. This reads the button, and then we can ask if it's the same. We don't do anything. Otherwise, we see if it's changed, if it's been pressed, or if it's been released, and we call the event send. We send the event to the machine. We send the button or the event that's specific to the push or the release. So that's that part. We did the events, we did the generic queue, we did main. The file I/O, this is another machine. It's basically a switch statement saying, here's the initialization. The first thing that we do is we set our speed to 4. We kickstart the events by pushing the next word event in. We call a function that sends the next word. This is shared with the other part 2 code. And we restart our time. We don't restart our timer this time. When the interrupt happens at the end of the transmission, we're going to start our I/O timer. When the timer is complete, we're going to post another event in that says go do the next word. The buttons, when we press the faster or slower, send an event faster or send an event slower. And then the file code here figures out what speed it should run at. In the polled mode, we do everything in speeds of low, medium, and high. In this code, we do 10 levels of speed. So that's that part. The other would be the GPIO. We could talk more about that. Where is that? That's here. So in the GPIO case, we've got a little data structure that we handle for each one of the buttons. Here's our left button. This is the GPIO information associated with it. It's bit 2. And this is, we only send the press event. This is the machine to send it to and the event that we send. We've got another example down further. This is the up and down. This is for the LED. And then we have the ability for debugging, reading a button by name, or we can read the button itself. Some more debug code. Here's initialization code. And more debug code. Then we get to the interrupt handler, which just is basically the Xilinx code. And then in part 2 code, we don't do anything, we just set a flag, and it's handled in the polling loop. Otherwise, we go through our array, figure out which buttons have changed, and if the button has changed, we send an event to the button machine saying that this button has changed. What's unique about our design is that we can handle multiple buttons at the same time. Ali says I'm talking too much. Okay, let's run. Yes, I'm getting going now. So we're now going to run. We have our little test code. Here is, we press number 3. We say, this is my big file. It's going again. And let's see, we can make it go much slower. And now we're going to make it go much faster. And that's that for this part.